Okay, one more time. The project that we have is a 225 amp kVA transformer coming from Excel, feeding a 500 amp panel in our building through two sets of 4 conductors, 250 kcm. The voltage is 28120. The impedance is 4%, 3-phase. The length between the transformer and the main panel, Kerry, my friend, is 50 feet. The length between the main panel and the lighting panel is 20 feet. The conductors feeding the lighting panel is 4 out, main lugs only. And my job is to size the do the short circuit calculation and find the interrupting rating of the circuit breaker. I need to find the interrupting rating of this circuit breaker, and the withstand rating of these 2 panels. Cool? We haven't done that before. This is new. Today we're going to do it by hand. Next week, you guys are going to grab SKM and use SKM to do it. So you would never use this again, unless you are in a contractor who does not have, work for a contractor who does not have a calculator, a software, then you're going to be using it. Okay, any question, guys, about what's given? Any question about what's given? So what I need to do then, I need to find the short circuit at point 1, the short circuit at point 2, the short circuit at point 3. There's 3 different locations. So, Joe, my friend, if you grab phase A, phase B, phase C, and bolted them inside the lighting panel, how much short circuit current you're going to see? That's what we're going to calculate for point 3. Then, if you went to the line side of this circuit breaker and you bolted phase A, the phase B, phase C, bolt them, and how much current you're going to see at point 2? And if you went, and then these are separate, right? We do this calculation separate, not at the same time. And we're going to go to the line side of the transformer, take phase A, phase B, and phase C, tie them together, and flip the switch on the transformer. How much current we're going to get? Cool? Short circuit. Short circuit. Okay, so let's go ahead and start. I'm going to start first of all, at point 1. I want to say, everybody understand before I go ahead, guys, and do this calculation? Everybody understand what we're trying to achieve? Cool? Trying to achieve short circuit at the 3 points. Okay, so keep in mind what the impedance and everything else. So I want to start by saying, let's go to, first of all, I want to say 1, which is at point number 1, right? 3-phase at point number 1. Here's what you need to do. You need to take I short circuit 3-phase. I short circuit, we're doing 3-phase short circuit. Cool? Everybody's doing 3-phase short circuit. I 3-phase short circuit equal, so that's the one that you need to do. The formula that you need is I XFR divided by the impedance. That's the formula that you need to find the short circuit there. No problem, Chad. So let's go find, then the next, you need to find I XFR, the full load current of the transformer, guys. How do you find a full load current of a transformer? I have 225K divided by 1.73 times 208. Joe, my friend, any reason why we multiply by 1.73? 3-phase, right? That's a 3-phase. So that's how we find the short. First, you find the full load current of the transformer. I haven't done the calculation, so I need somebody to do the calculation with me. So let's take 225 divided by 1.73 divided by 208 multiplied by 1, 2, 3. I came up with 625. I have 625.3 amps. I need a second. Can you guys please give me a second? Second? Okay. So because I don't have the answers for these, this is no. The full load current. So Darren, my friend, this is as easy as just finding the full load current of the transformer. Really nothing, no big deal. No big deal, right? No big deal. Okay, no big deal. Then I'm going to use the second formula here and find I short circuit equal. Remember that it says the I XFR divided by Z impedance. Okay, so that will give me 620. Did they say 5? 25.3. Divide this by, what's the impedance? Anybody? 4%. So what's the 4? 0.04. And what do you get? 16,000. So 16 point. Now we put them in case. So that will be, you come 16. I came up with 15. Yeah, 15.6, right? Okay, 15.6. So that will give me 15.6, give or take, right? Kiloamp. Oops. Kiloamp. So the short circuit, guys, at the terminal of the transformer is 15.6 kiloamps. Any comments, any questions? See how easy that is? That's it. So at point one, the short circuit is going to be 15.6 kiloamps. 15.6 kiloamps. If we did the math right. Right? Adam and I did the, anybody else that came up with a different number, please second it because I don't have calculation. Okay, so point one is done. Completely done. Any comments, guys? We've done this before. This is new. Point one is not new. It's not, it's not new, really. We've done it before. Hey, so let's go to point two. Let's go to point two. I want to remind you, for short circuit, Joe, and since you're my friend today, for short circuit, guys, do you expect the short circuit right at the terminal of the transformer were 15.6? As I move 50 feet of cable, do you expect 2 to be less or more? The short circuit at point 1 is 15.6. As now right at the terminal transformer, when you put cables are impedance, they choke the current. As you move 15 feet away from the transformer, do you expect number 2 to be more or less? Less, thank you. To be less. Why less? Because when you have cable, Adam, the cable acts as what? Impedance. It chokes the current. Can I have thumbs up, Chad? We fully understand that it chokes the current. Cables will choke the current. So as we move from point 1 to point 2, the cable will choke the current. The cable will choke the current. So point number 2 will be less. Point number 2 will be less. Cool? But by how much? By how much less? That's what we're going to calculate. By how much less? That's what we're going to calculate. Okay. Any question, guys, before I go to point number 2? Point number 2 is going to be piece. Number 1 is piece of cake. So I'm going to go to point number 2. So 2, short circuit at point number 2. Short circuit at point number 2. Short circuit at point number 2. Here's the formulas that you have to use, and these are a couple of formulas. Write them down. Bring them to the test when we do the test. I don't care. Because they're a little bit interesting. There's a factor. The formula that we're going to use, guys. Step number 1 is the F factor. The F is not for the F word or anything. It's called the F factor. The F factor formula is the following. The F factor. Now, Adam and Joe, my friend, because of the impedance of the cable, we need to accommodate for the impedance. So the impedance is going to choke the current. But by how much? The F factor will get you by how much? Cool? So let me write the F factor. It's in your book too, and also we use it all the time when we do training for safety training. This is, if you work for electrical contractor, that's their Bible too. So F factor formula is the following, my friend. Is it three phase? 1.73 times, that's for three phase, times L times, and I'll explain this in a second, times I three phase divided by I three phase short circuit, three phase short circuit divided by C multiplied by N multiplied, and I'm sure you're looking at by V, the voltage, multiplied by the voltage. Cool? Multiplied by the voltage. So let's just see what the heck are these before we go ahead and do it. I'm going to define them for you. L equal length. 2. V, of course, V, voltage line to line. Voltage line to line. C, this N, number of parallel runs. Number of parallel runs, if I spelled parallel right. And C is conductor factor. And you're going to see what the conductor factor is. C, they call it the conductor. I'm going to call it conduct. C stands for conductor factor. Conductor factor.
Is it N or M?
This is N. N. Yep. N for number. N for number. Number of parallel conductors. I think parallel is EL, right? Here's we'll spell it. Okay. Parallel conductor runs. Number of parallel runs. Yep, parallel runs. Okay. Any question about this F factor? It's a factor. Why F factor? Cool. Now, why do we care about this one? We care about it because that's the percentage that you're going to cut the short circuit by that's coming from the transformer. That's what you're trying to find. What's the percentage that you're going to cut the short circuit by that's coming from your from a transformer to your building? Any questions about this? So this is I. Yeah, let's put the I. So do we have N, V? Let's put I as long as we're on it. I short circuit. This will be short circuit current three phase. Short circuit current three phase, or three phase short circuit current. Cool? Three phase short circuit current. Any comments, guys? Any questions about that? Shall we go plug the number in?
Conductor factor is a set number.
Thank you. Conductor factor. Good point. Everything is, you guys familiar with everything except what the heck is a conductor factor, Chad? Conductor factor, for you, it will be coming from table, for conductor factor, table number 16-3, page 426. 426. You're also right, buddy. Let me write it with different colors. Factor. So this would be table 18-3, did I say? Table 18, thank you. Table 18-3, and the page in our book is, what did I say? 426. 426. Everybody guys go there and look at this table, please, because we're going to be picking up information from there. Page 426. This table will give you the value, the C value, right? The C value for all the conductors that you're going to be encountering. For all the conductors that you're going to be encountering. Okay? Any questions, guys, about this? Any questions? conductor factor, the conductor factor. Conductor factor. Okay, let's go plug it in, shall we? Any question about this? Carry L length, N number of petal runs, C the conductor factor from this table, I is the short circuit, right? Is there anything else that you guys need to know? Cool, we're good. Okay, so let's go plug in the numbers, right? Let's go plug in the numbers. So I'm going to say here, we're still doing point number 2 to continue. This is point 2 to continue. I'm going to go F factor equal 1.73 times. 1.73 times, what's the length? What's the length for the run? What's the length for the run? 50 feet. So I have 50 feet of length. Okay, so let's go put the 50 feet. So that will be 50 feet times. What's the short circuit, guys, that we just came up with? The short circuit, Adam? The short circuit that we brought just a second ago. It's 15.6. So 15.6. We're going to put them 15.6. We're going to cache them though. We're going to cache it. It's 15,600, right? That's 15.6. We're caching it. Divided by, Carry, my friend, how many runs of right? Did we get it right?
I know what you're saying.
Cache when, yeah, the K, instead of putting in K, we cache the K, we multiply by 1,000. Cool? Okay, when I say cache the K, because we don't want to put in K here. You want it, and you cache the K. Okay, 15,600. Okay. Now, number of runs. What's the number of runs? So did we do the C factor first? Okay, the C factor. For the C, let's do the C factor first. Can you guys go to table C, please? Can you go to table C? Value C table 18-3, page 426. 426. Everybody's there? Okay. Now the size of the conductor that we're pulling. Everybody understand the size of the conductor? What was the size of conductor here? The 250. The size of the conductor is 250. Okay. So do me a favor. Who's going to be the A student who can give me 250 kcm? If you guys look at, there is copper conductors, 3 single-phase conductors, in a steel conduit, in non-metallic conduits, and in copper conductor, 3 conductor cable. Okay, now I need to emphasize one little thing here. Now, Carrie, my friend, we're coming here from underground. We're coming from underground. So what type of conduit we're going to use? PVC. So I need to use PVC here. Here's my PVC. I'm using a PVC. Cool. Everybody understand what we're using coming from underground? PVC. So that will help us find the C. Okay, so we're going to use non-magnetic conduit. These are the PVC. Can you guys write yourself a note? These are the PVC. Then our system is 600 volt or less, right? Yep, 600 volt or less. I need the multiplier for 250 kcm. What's the multiplier for 250, please? Anybody can verify the multiplier for 250?
18,593.
Thank you. 18,593. Everybody can see that? Everybody can see that? Anybody does not know how to get that factor?
So you'd be using 15 kV.
No, we're using the 6 kVA. It's the 600 volt. The first decision that you need to make is it metallic or non-metallic? Is it copper? First of all, all these are for copper. Is it metallic or non-metallic? Right? We're non-metallic, so go to non-metallic. Next, is your voltage 600 volt or less? Then you use 600 volt, right? Otherwise, if it's higher than 600 volt, you use the others. Kerry, does it make sense? 5K and 50K.
What's the difference between conductors and conductors?
These are cable or conduit. 3 single conductors in a conduit or 3 conductors in a cable. Good point. Conductors, copper conductors, 3 conductor cable. Can you see at the top 3 conductor cable? Everybody understand how the table goes? There's cables and conduits, 2 sides. Under the cables, you have steel conduit or non-metallic conduit. So you're pulling a cable or you're pulling conductors. Everybody understand? We typically pull, Andrew, my friend, we typically pull what? Conductors or cables? What do we pull, Andrew? What do we typically pull for feeders? We pull cables inside conduits or conductors? Single conductors, right? We pull single conductors inside the conduit, right? Okay, so what's my multiplier for 250? 8593. 18593. 18593 times. Any question, guys, about the 18593? Any question about the 18593? This is your multiplier coming for this particular cable. For this particular cable, for 3 conductors in 1 PVC conduit. If you put rigid, it's going to be, if you're using rigid or EMT, you're going to use for you're going to go under steel conduit. Right? Can I have thumbs up, Chad? We know how to use the table first. The table? Yes? No? Darren, my friend? Cool? Joe? Okay. So that's how we use the table. We got this number. Then, N. So that's the C factor for the conductor. What's the N? N is the number of runs. How many runs we're using? 2. Thank you. We're using 2 runs. Okay, the loss factor is what? The V, the voltage. What's the voltage, guys? The voltage is 2A. Line to line is 2A. Now, I don't have this value, so I need one of my friends here. 50. You got it? Divided by. What did you come up with? 0.17. 0.17 it is. 0.17 it is. Okay, 0.17. So this factor is 0.17. I'm going to use 4, guys. This is my F factor. Thank you. My F factor.
The same as like 17%.
You're going to see in a second. Just hold your horses. Yeah, you're going to see how this is translate into a percentage. You're absolutely right. But there's one more step to do, translate into percentage.
So do you always want us to carry it out to 3 decimal places?
Do 3 decimals for this particular one. Okay? Any question, guys, about calculating this? That's piece of cake. Now, there's an M factor. M for multiplier. The M factor is defined as, we need to find also the M factor. M factor is defined as, my M factor is 1 over 1 plus F factor. Look how easy that formula is. Now, Darren, this is your percentage. The M factor is your percentage. So can you guys plug it in? 1 over 1 plus 0.174. So I need 2 gentlemen to agree on one answer. 1 divided by equal 1.174. What did you guys come up with? How much? 0.85. Second? Okay, 0.85. So this is a 0.85. Darren, this is your percentage. This is your percentage. Any comments, guys? Any questions? This is your percentage. Any comments? Any questions? Any comments? Any questions? Guys, NEC 2011. require all service entrance panels to have a short circuit rating. That's as of 2011. What does that mean to you and your company? Means you guys are going to be doing this calculation, or you're going to hire an engineer to do the calculation. There are two ways of doing it. If you don't have SKM, which you have to pay close between $10,000 to $40,000 to have it for your company, there is a method that you can do an approximate value by hand. Cool? Since we don't pay for it at Dunwoody, you guys next week, you're going to be doing this with the software. But what I'm hoping this week is we make you appreciate all this calculation that we do. If you don't have the software because it's expensive, that's how you're going to do it. Cool? Okay, so the last step, my friends, now the last step is three-phase short circuit. Now remember, guys, at which point? Equal Joe, my friend, this is the three-phase short circuit at what point? At point 2. So this is how the definition. M multiplied by I short circuit, three-phase, same thing, all these three-phase. So I, just do the same terminology, I short circuit three-phase. This is at which point? Can you guys write yourself a note? This is at point 1. At point 1. So that's your percentage that you're going to derate. This is at point 1. This is at what point here? This is point 2. This is at point 2. This is at point 1. Okay, now the multiplier is 0.85 multiplied by 15.6K. Gentlemen, what's the answer? 13.3. Do I have a second? 13.3. Do I have a second? Yeah. Okay, so that's 13.3 kilo amp. Now, Joe, can you see that it knocks it down almost how many? Like almost 2, like a little bit more than 2 kilo amp. The cable knocks the short circuit down 2 kilo amps. Why? Because of the impedance of the cable. The impedance of the cable. Any questions, any comments? Any questions, any comments? Okay, so I'm going to go back here. I'm going to go back here, and I'm going to write the following, my friends. I'm going to write the short circuit right at this point was 15. Oops, let me use a different color. The short circuit right at this point was 15.6K. The short circuit, oh no, not this point. The short circuit at this point was 13.3 kilo amp right here. The short circuit right at this point, guys, well, what? It was 15.6 kilo amp. Can you guys see it started right at the terminal transformer 15.6? We dropped it down to 13.3. Do you see the advantage of having sub-panels away from the transformer or the main panel? You have less short circuit. We dropped it down, not substantially here, but if you have a bigger system, a longer cables, you will drop it substantially. What's the problem with longer runs, guys? This is the advantage of having the cables far. What's the disadvantage there of having a longer cables? Voltage drop. So you have two things you're juggling. You're trying to move your panel far away from the transformer so the short circuit goes down, and at the same time, you're trying to get it closer so the voltage drop goes acceptable level. So that's where you have to find the happy medium between them. Okay. Any question, guys, about, so we found it at 50.6 at point 1.2. Gentlemen, we're going all the way to point 3. We're going all the way to point 3. Any comments, any questions before we go to point 3? Any comments, any questions before we go to point 3? Aaron, my friend, did you caught up? I know you came at the end, the tail end of it. Any comments, any questions about the point 1 and point 2? I'm going to go ahead now and do the calculation, the same calculation, guys, at point 3. The same calculation at 0.3. Now, at 0.3 carry, my friend, I want to remind you the distance is 20. The cables are 4-aught. Do we have, how many runs do we have? One run. Okay. One run. Okay, let's go do it at point number 2. Point number 2. 2. Okay. Point 3. Short circuit at point number 3. Short circuit at point number 3. Anybody can guess what we're going to start with now? The effector. We're going to start with the gain, the effector. So let's go write the effector. You guys see, we're going to repeat these steps. Remember these steps here? We're going to repeat these steps. We're going to repeat these steps. Cool? We're going to repeat these steps. So I'm going to have the effector first. So let's come over here and say effector equal 1.73 times L times I, 3-phase, times I 3-phase, divided by C times N times E, V. I use the V, times V. Now, the only thing I want to remind you, I 3-phase here, this 3-phase value is at, can you write yourself, guys, at 0.2. This value here is at 0.2. Because now we moved away from 0.1. This is at 0.2. At 0.2. Right? The first, you guys remember this one here was at 0.1. We got it from 0.1. Now we move into 0.3. We go back to 0.1 and find the short circuit at 0.2. Okay, who's my favorite friend here? That's going to have the effector. Again, 1.73 times. What's the length? The length, yeah, 20 from the main panel. The length, not from the transformer. Not from the transformer. Can you guys see that? Your length not from the transformer, your length from the main panel. Mr. Kojak?
Can you see you're okay? I haven't heard from you for a couple days.
I'll visit with you later. Thanks. So the length is not, you don't add the 50 and the 20. You just use the 20. Can I have thumbs up, Chad? We know that you use the 20. Okay. So we're gonna go to the 20, go back, or forward. Okay. So the L is 20 times, what's the short circuit at 0.3? At 0.3. At 0.2, I'm sorry. 13,300. Again, cache the K or multiply by 1,000. Cache the K, multiply by 1,000. Divide by, okay, let's go C. Find C, please. Let's go find C for 4-aught. Now, Darren, I want to remind you we're inside the building. What type of conduit typically we use inside the building? EMT. EMT is it's called magnetic here. Okay? So you're going to have steel conduits. You're going to go to steel conduits, right? So let's go 600 volts, steel conduit 4-aught. Anybody can give me an answer? 15,820. Anybody does not know why we went there? We're using EMT because we're inside the building. 15,082. Thank you, sir. 15,082. So we're using 15,082 multiplied by. And how many runs are we shooting? What? No. Not conductors. Parallel runs. 1. See, that's a 1. The conductors are 4, but the sets, how many sets are we running? 1 set. 1. 4. Multiply by what the voltage? 2 equal. I need 2 gentlemen or a gentleman and a lady to come up with an answer.
.147.
What did you come up with? 0.147. You approximate, right? 0.147. 0.147. Thank you. Adam, you got your milk today, man. It's funny here. Good, thank you. You gained your 10 out of 10 for participation. After we do the F, that stands for fun factor, not the other F. We need to go find the what factor? The M factor, right? Remember how we find the F factor first? Here's a F factor. Next is going to be the M factor. So I need to do the M factor now. M equal 1 over 1 plus F. And this one piece of cake, 1 over 1 plus 0.147. 1 over 1 plus 1.47. Not 1.47, Chad. 0.147. We'll get it. Okay. Two people give me the same answer, please. Yep. How much? 0.87 second. 0.87. Darren, my friend, this is your percentage. This is your percentage, gentlemen. This is your percentage. The last step here is to find I short circuit 3-phase at what point? At 0.3. So you'll take the 0.87, multiply it by I short circuit at 0.3, 0.2, which is 13.3 K. Everybody knows where this short circuit came? The one above it. The one above it. Any take? $11.87 times 13.3, 11.57, right? Yeah, 11.6. Thank you. 11.6 KA. Thank you. 11.6. Yeah, you don't want to go the 2 decimals. 11.6. Any comments? Any questions? Any comments? Any questions? Any comments? Any questions? So that's how we calculate the short circuit. That's how we calculate the short circuit. What I'm going to do, guys, I'm going to give you a 5 minutes break, and I'm going to do one more example for a 480 system, and then we're done with the short circuit calculation. Cool? One more example, 480, and we're done with the short circuit calculation. So I'm going to go back before I do that and put 11.6. My panel right here, is 11.6 kilo amp. Can you guys see that we started with 15.6? We dropped down to 13. We dropped again to 11.6. And all this drop is happening because of what? The impedance of the cables. The impedance of the cables. I'm going to take a 480 system, gentlemen. We do the same calculation for it. So stick in, and then we're done. Cool? 5 minutes. Okay, let me see here. So this is number 2. This is 2 as an example number 2. I have example number 2, my friends, and I need to do the following. I need to do calculation at 0.1, calculation at 0.2, and calculation at 0.3. 3 calculations, same way we did it. Same way we did that calculation. The only difference this time, I up it to 1,000 kVA, not KCM here. This is 1,000 kVA. Oops. VA, 1000 kVA transformer, 48277, three-phase. The impedance of this transformer is 3.5%. The conduit, so I sized the system. You guys are going to be sizing a system. This transformer is feeding 1600 amp panel. The 1600 amp panel is feeding another 600 amp panel through main lugs only. Main lugs only panel here. I have 4 sets in a 4-inch PVC conduit, 4 conductors, 600 kcm copper. For this feeder, I have 2 sets, 3-inch EMP conduits, 4 conductors, 350 kcm copper too. And I need to find the short circuit rating of all these equipments. I need to find the short circuit rating of all these equipments, the withstand rating for the equipment, and the short circuit rating of these equipments. I'll give you, this is panel P1 as well as P2. You can call them any name you want. P1, P2. Kerry, let me know if you want me to read any of these things for you. My handwriting is, if you write better than me, you'll be a doctor, right? Is that what the doctors write? Like, that's exactly what I say. If you write worse than me, you are a doctor. Okay, any question, guys? Feel free to. I can read any one of these for you. So. Give you a few seconds. Now, Aaron and Zach, I know you guys came a little bit late in the first example. You can follow. We're going to repeat the same questions. So that will be a good start, huh? It's hard to come halfway through.
Got most of it.
You got, okay.
Well, I was reading the book while you were talking.
Okay, let me know when you guys are ready. Take your time, but not a biggie. When we do short circuit calculation, guys, we do line to line. Line to line, for the most part, is the worst scenario. When you grab phase A, phase B, phase C, you bolt them together and you flip the switch. That's the worst scenario that you're going to encounter. Line to ground and line to line, 2 lines together, and line to ground almost always will be lower than the 3-phase. Sometimes it's not true, especially for the ground fault. But for the most, if you size based on the worst scenario, which is the 3-phase short circuit, you are covered for 90% of the situations. 90% of the situations. Okay, let's go ahead and start so I'm gonna, the first thing I need to do, this is 1, short circuit at point number 1. When I say short circuit, I always mean 3-phase short circuit. Okay, this is piece of cake. You guys remember, first you find I, X, F, R, full load current for the transformer. I have 1000 kcm. Divide this baby by 1.73 times the voltage is 480 volt. I don't have the answers for these, so I really would like somebody to second me. Or do the calculations. So I have 1000 divided by 480 divided by 1.73 equal. Anybody? $12.04. Any second? Good. 12.04. Thank you. 12.04 it is. 1204 amps. The full load current of this transformer is 1204. Cool? That's a piece of cake. No gimmicks, nothing. Right? Nothing to it. The second, I'm sorry, did I? 0.2? 1.2, then you didn't multiply by 1000. There's a K.
Oh, 1000.
Yeah, there's a K. Did we say cash the K? You guys use the term cash the K? Like it's the dollars, you know. I have $1 kilo is $1,000. Cashing it. Maybe it's chance technology, definitely, huh? I short circuit 3-phase at point number 1, right at the terminal of the transformer. Right at the terminal of the transformer. piece of cake, Chad. The rule is you take I XFR, the full load of a transformer, divided by the impedance. So 1204 divided by the impedance is 0.035, right? This is 3.5%. Is that what I said? 3.5%. So yep, 3.5%. That would be 0.035. And I need my favorite friend to give me an answer. 34.4. You approximated, right? Okay. Kilo amp. I need a second, please. Second. Thank you. See how big the short circuit now? How big the short circuit? It got bigger. Can you guys see the lower the impedance, the higher the short circuit? So when you have high efficiency transformers, that's low impedance. What's the drawback of these high efficiency transformers? High short circuit. High short circuit. Okay, at point 1, we got it at point 1. So I'm going to go here and say at this point is 34.4 kilo amp. 34.4, right? Now let's move down. I want to go to point 2. For point 2, we need to find the F factor and the M factor. So point 2, let's go down to point 2. So I'm sorry, am I going too fast? Am I going too fast, gentlemen? Yes, no, Joe? Cool. 1204. That's the full load current. 1204. 1,204 amps. It's a big boy. It sounds like it's a big boy. Now, some of you guys might wonder, look at that. The full load current of the transformer is lower than what my panel is rated for. That could be typical. The utility control the transformer, so they give you a size typically 25 to 50% lower than what you ask for. So that's typical. If you look at my panel is 1600 amp, but my transformer full load current is 1200 amp. So what happened to the other 400 amp, Chad? The utility guys call the calculation that we do is architectural calculation, and based on their statistical data that they collected over the years, they're smart. They have more data, not smarter than us, but they have more data than the engineering firms. So when they come up with a value, they really statistically they can prove that your building that you think it's 1600 amp, really in reality is not going to get 1600 amp, because they have hundreds of buildings around the town, the same size, and they're consuming 50 to 70% of what you size for. Okay?
Even if you turn everything on, you have everything running, it's still overloaded.
You want to load it. You never load it. You know why? Because remember when we sized for motors, what did we do for the full load current of a motor? Multiply it by what? But these are not real. They're for safety factors. Imagine all these safety factors, keep adding them up at the service. You end up with a lot of, at least 25% oversized, 25 to 50% oversized system is typical for future safety and all this stuff. Now with the utility, if say in the future you grow and you start sucking more than that transformer, you know what they do 10 years from now? That's it. Your cables are there, they just put another transformer for it. So this is typical. This is typical, my friends. So, okay, so let's go to a point. Can I go to point 2? Everybody's good with point 1? All right, let's go to point 2. So point 2, short circuit, of course, always 3 phase at point number 2. At point number 2. F factor. F for fun, not for the other F. The F factor. So let's go write the formula for my F factor. My F factor is 1.73 times the L times the I short circuit at which point, guys? Three phase, right? Three phase at number one, write these divided by the C, the N, and the V line to line, the voltage line to line. Start plugging them in. Effector equal. Okay, right? This is the formula we wrote it before. That's the formula that you need. Effector equal 1.73 times, what's the length? 400 feet, right? That's just to the panel. 400 feet times, what's the short circuit at point 1? We just calculated that one. What was it? 34,400. Right, Adam? 34,400. Divide by, okay, C. Let's go find C. I want to remind you, my friend, C is C is going to be for a conductor. Here's the conductor that we're pulling. We're pulling 600 kcm, 4 sets of them, 600 kcm. So can you guys find it? And it's PVC. So non-metallic conduit, PVC, 600 volt from table 18-3. You're going to find for 600 volt. Anybody can help me read the number? 28,033. Anybody disagree? Anybody does not know where this number came to be? These are, guys, tabulated and calculated from impedance for the cables and so forth. So they're already tabulated for you. Otherwise, you're going to have to do a lot of calculations. So it makes it easier. Okay, so 28,033. 28, okay, 033. So this is a 28,033 times. Aaron, my friend, how many runs are we shooting for? Thank you. There's no camera here, so I can point to you for. What's the voltage? Line to line, always. The voltage is 480, right? 480. Gentlemen, I need 2 gentlemen to give me one answer, please. A second? Did you do it? Yes? Okay. 0.442. Thank you. 0.442. Any third? Do it? Okay. All right. So let's go to the M factor. The M factor equals 1 over 1 plus the F factor. So that's easy. 1 over 1 plus 0.442. I need 2 people to give me the answer for the M factor, please.
59%.
How much? Second? Do I have a second?
Yep.
Okay. Did you guys see it now? Where's Darren? Here's your percentage for cutting that short circuit. The impedance have been cut down to 69 because of the length of the cable. I mean, the short circuit have been cut down to 69 because of the impedance of the cable. 400 feet run is a long run. Can you guys see how it's cut way sharp? Deep cut because of the long. The impedance will act like a fuse, guys. Choke the current. Choke it. Cool? I'm the doubting Thomas. That's all. Because based on this factor, everything will be wrong. You know what I mean? If you make a mistake here, all your calculation downstream will be wrong. Okay, the last thing we need to find is I short circuit 3 phase at what point? Point number 2. Oops. Wow. At point number 2. At 2. I'm going to say just at 2. Gentlemen, this will be M times I short circuit at 1. That will get me, what's M? 0.69 times Or is it 34.4? 34.4 K equal 23.7 second, thank you. 23.7 kilo amp. 23.7 kilo amp. Gentlemen, we got point 23.7. So you're going to go here, right at this point, it's 23.7 kilo amp. Right at the line terminal of the transformer, of the line terminal of the overcome protection device, the main. Cool? Point 3. I'm going to give you time to join the second here. Point 3, I want to show you guys point 3. 2 sets, EMT, not PVC, and 350. Okay? So let's go back. Okay? Let me know, guys, when you're done with this. Cool? All right. Can I go? Move? Yes? Okay, good. Let's go to point 3. 3. Short circuit at point number 3. Short circuit at point number 3. Short circuit at point number 3, guys. The first thing you need to do is what? Mr. Effector. 1.73 times. Since we don't want to write the formula again, times. What's the length? 200 times the short circuit at point. Now here's the key point here. The short circuit, and maybe we should write it down. It doesn't take much. Okay, so if you take so 1.73 times L times I, short circuit, 3 phase at 2 divided by C times N times V. Piece of cake right in here, F equal. Now we can get rid of this book here. So 1.73 times, what's L? 200 times, what's I short circuit that we just came up with? Is it 34? 23? 7. It's 23,700. You have to catch the short circuit here, guys. So divided by, what's the C? Let's go find the C for what size conductor? What size conductor? We have a size of conductor, guys, as 350. What's the C for 350? C for 350. EMT, non-metallic, so steel. 350 steel. Anybody? 19,529. Second? 19,529. 19,529. So that will be 19,529 times. How many runs are we going to the second panel? 2 runs. Thank you. What's the voltage? Still the same voltage, 480. 480 volts. Now I need 2 of my favorite friends to give me the answer, please. And I need agreement. Start to 0, 0. Okay. Anybody? How much? 0.437. 0.437. Gentlemen, you got it. 0.437. The M factor. Piece of cake now. M equal 1 over 1 plus F. 1 over 1 plus 0.437. I need two gentlemen to agree on that. 0.7? 69 point,
3 or 2 places.
point two places. 0.70. Okay, 70%. Cool. So that's my M factor, my multiplier. The last step, my friend, is I short circuit 3-phase at 3 equal M times I short circuit 3-phase at 2, and this will give me 0.7 times 23.7 K, and that's the answer. What's that? 16.6 kilo amp. 16.6 kilo amp. Any comments, any questions? Any comments, any questions? Any comments, any questions? So let's go back and size. Let me just, when you're done. So that'll give you 16.6 kiloamps. 16.6 kiloamps. Any comments, any questions? Okay, now I'm going to go back. I'm going to go back 16.6, right? So 16. Now the question would be, Kerry, my friend, why do you give a damn? Why do I give a damn to all these calculations? Right? You don't? No problem. We'll send it to the engineers. We'll do it for you. We'll charge you for it, right? You won't have to do that. Well, you have to care for Chad now, at least. So why do we care? Why do we care to do all this? We need to size the interrupting rating of the circuit breaker and the withstand rating of the equipment. So based on this, here's what I want you guys to do. I'm going to go use black, color black, and looking at 23.7 kilo amp. What's the next standard interrupting and withstand rating for this equipment? Let's say, obviously, we're going to go find a circuit breaker and a panel that can withstand 23.7 or more. 23.7 or more. Okay? 23.7 or more. Let's just assume based on this value, guys, I'm going to go find at 20, I think they make 22.7. The next standard, let's say 35. I'm going to be using a 35 kilo amp panel. Based on this value, 23.7 kilo amp, I'm going to be using a 35 kilo amp circuit. So the withstand rating of this panel is 35, and the erupting rating of the circuit breaker is 35. Would that be able to handle 23.7? Yes. If I have a standard 25, would I use that 25? Yes. I'm picking 35 kilo amp because it's standard. Now let's look at this panel here. This is 16.6, right? Look at the 16.6. So then 16.6 right in here. So based on this panel withstand rating can be 22.5 kilo amp. I can use the 22.5 kilo amp right here for the 16, right? For the 16, 22. But the circuit breaker here, though, my circuit breaker here, because because the short circuit here is that value, the circuit breaker here is going to be 35 kilo amp. 35 kilo amp. The circuit breaker inside the panel will be 35. Everybody knows why the circuit breaker will be 35, but the panel itself rated for 22.5K, because the panel, based on this scenario, my panel is way far away from the circuit breaker. And it's the short circuit have been choked. Now, is it wrong to go find a panel that can withstand 35 kilo amp? No. What's the drawback? Cash, money. That's why we did all this calculation, to find the short circuit, the withstand. There's two values. Interrupting rating for the overcam protection devices. That's called the interrupting rating. Short circuit, the interrupting rating. Short circuit withstand rating is for the equipment. when you shake these equipment and you heat these equipment, you need to be able to withstand this heat and this and the heat as well as the magnetic force that doing this equipment. Next week, Joe, my friend, you will be doing the same calculation, except instead of doing it by hand, you're going to be using a software called SKM-PTW. The last thing I want to talk about, guys, is what happened to the ground fault. This is three-phase short circuit. Your ground fault is almost always less than that. So when you deal with short circuit, there are three types of short circuits. Phase to phase, the worst scenario. You bring phase A to phase B to phase C, you bolt them with a piece of copper together and you flip the switch. That's as bad as it gets. The second one is phase to phase. Instead of three phase together, phase to phase, you case phase A and phase B, bolt them together, flip the switch. That will give you typically 87% of the value for the three phase. So it's, if you cover the 100%, Darren, would you worry about the 87% of that? You already covered. The worst scenario is covered. So phase to phase, typically 87%. Now phase to ground or neutral, that's a ground fault. Phase to ground or phase to neutral, that will typically 25 to 100%. So if you're covered for three phase, you're covered for all of them. If you're covered for three phase, you're covered for all of them. Can I have thumbs up, Chad? We fully understand if you're covered for three phase, you're covered for all of them, right? Adam, Andrew, are you guys with me? Joe? Okay, so that's what you get your short circuit. If you're covered for three phase, you're always covered for all of them. The last thing I'm going to talk is about, guys, is coordination. We'll talk about the coordination in this one. So that will cover basically that short circuit. If you're doing if you're doing single phase, Darren, if you're doing single phase, this 1.73 change into 2. Anybody knows why in single phase we have a 2? Because we have 2 conductors versus a 3 phase we have 3 because we have 3 conductors, right? Typically. So if you're doing single phase like 240-120, you convert this 1.73 just 2. Same calculation. Same calculation. If you're doing line to neutral, the voltage instead of 480 here, if you're doing it line to ground, you use 277. Same formulas. If it's single phase, 2, and you use the voltage, which is 277. Any comments, any questions? You guys, typically we deal 3-phase system. We are dealing with 3-phase system, so these are the formulas I'm going to be using. These are the formulas that I'm going to be using. The second thing I wanted to talk about, guys, is sometimes the impedance, you guys see that 3.5. So, Zach, if you look at the book that we have, they multiplied the 3.5 by 0.9 because the impedance is plus or minus 10%. They don't know exactly what the impedance of the transformer, the exact value. So they give you a value and it's within plus or minus 10%. So some engineers, they use this value and cut it by 0.9 to use the worst scenario, which is the smallest impedance, and you use it in the calculation. So if you see them in our book using right in here, if you see them multiplying right here 0.9, that's because they're cutting the impedance by down to 0.9, 10%. Okay, we didn't do that. You can use also this one as a value. They're cutting it by 0.9. So don't get confused where the heck this 0.9 come to be. That's because the impedance is plus or minus 10%. Plus or minus 10%. Okay, I'm going to give you guys a problem as a homework for this math. And I'm going to write them right here, please. And that will be it. So here's the system that I would like you to do. I have a transformer. Homework. I have a transformer. Here's my transformer. I am pulling an overcome picture device from this transformer. And this transformer overcome picture device, I'm pulling another overcome picture device to feed the second panel. And that's my second panel. Same thing, guys. I want you to do the calculation at point 1, at point 2, at point 3. I want you to use let me use a realistic transformer so we don't get into issues. I would like you, my friends, let's use a voltage. The voltage I'm going to burn this one is 243 phase. It's a 243 phase transformer. 243 phase transformer, and I need to find that the size of this transformer is 750 kcm. The voltage is 243 phase, and the full load amp. This guy is, we're using a 2000 amp here.
I just want to make sure.
2000. KC.
We did that earlier too.
Did I? The other transformer? I'm just stuck with the KCM. KVA, thank you. KVA. There's no KCM transformer. So KCM, thank you. And then 200, and let's use a panel, an 800 amp panel. 800 amp panel. And 800 amp panel. What I would like you guys to do, I want to give you the following. You need to size the system though. I would like this one to be, we use 400, let's use 300 feet here. And let's use this one as 150 feet, 150. And these are the feet. And I would like you guys to, I would like you to size. You have to size this and size this. You guys should be able to size it. The only thing I want to tell you is we're using EMT here, and PVC here, PVC. Okay, so you're going to size it. That's your system. You're going to size the cables first. So what you need to do is you need to find the size of the cable too. 1, 2, and find the short circuit. Find the short circuit. So the impedance. Impedance, let's use 2.5. 2.5% impedance. We're using a 2.5% impedance. It's an efficient transformer, 2.5% impedance. Am I missing anything? We have the impedance. You guys will size this conductor, use PVC. Which PVC, guys? Always use PVC 80. PVC 80, EMT for the feeder. And size that system. Any comments, any questions? Any comments, any questions? Yes, sir? You're going to size it. I have 2,000. How are you going to? Would you pull one run to 2,000? That would be a big. I don't think you can find a conductor anywhere. For the 800, you have to parallel. Both of them you have to parallel. The rule when we size, guys, always cut. You don't want to carry more than 400 amp in a feeder. So if I make sure that I divide this by 5, I will divide this by 2 and carry the conductors. Okay? Any comments, any questions, guys? This one? No, you don't need to know because it will be sized based on, it's an 800 amp panel. You don't need to know. If the overcome picture device is 800, the panel will be 800 amp. Good point. 800 amp panel. And I'm going to call this is P1, panel 1, and this is P2, panel 2. Now, here's my question for you. Whom am I going to pick on? Aaron, my friend, if I have a panel 3 and 4 and 5 and 6, you just keep doing the same thing. If I grab a feeder from here and go feed another panel from it, same thing. The only thing I did not talk about, guys, is the contribution of motors. Contribution of motors will contribute to it. That's a different topic. Any comments, any questions about this? Any comments, any questions? No, I don't want you guys to do chapter 18 homework. This is the homework for chapter 18. Cool? Everybody got that? That's your homework for chapter 18. This is homework for chapter 18. This is the homework for chapter 18. Because chapter 18 talks about the same calculation that we did. I still need to do a few things about chapter 18, but not today, guys. I'll pick a couple of certain, very simple things I want to talk about. Any comments, any question, guys, about the short circuit calculation? I can't emphasize, my friends, the importance of sizing, the importance of the sizes that you're going to come up with. Let me just go to the 480 system. Here's the 480, the same calculation, guys, you're going to be doing. Why do we care? Like Carrie said, not because she had asked you guys to do that, because if you don't have software, that's how you're going to be sizing it. Based on this, you're going to find the interrupting rating of these equipments. Any comments, any questions? Any comments, any questions? Okay, that's all I have for you guys. My expectation, guys, is you please print a clean copy of E1 through E10. So.
You want them on big sheets or small sheets?
Big sheets.